Okay, 5 minutes past 12. So I think as per 12, 1 minute. Okay, we wait another 1 minute because as requested by Ryan, 5 minutes after 12:01 p.m. Okay, I don't want to wait longer time because I think it is not fair to those who have already been enrolled or being joined earlier on. So I think those who left over, I think should be more aware about the class time. Right. So now it's 12:06. I think I want to start the class today. All right. So please pay attention to the slide, to the video, and should you have any question, please keep your question at the end of the every part. Right.
Assalamualaikum.
Good afternoon, doctor.
You can hear me? Okay. Azwan? Hello? Mungkin Azwan ada problem. Okay. Can hear dog barking. Okay, you hear me now? All right. Dr. Azwan is on.
Yes.
Okay, so this is the right room lah ya. Ada banyak pula room. So
Can you voice? Okay, not
okay, dah jalan ke belum video? Belum
Tak jalan tapi tak dengar je, tak dengar pula bunyi.
Mana dia punya tu audio tu. You
Sorry.
must stick the audio and use desktop. Jangan guna tu.
Dah.
Okay.
Alright, so those are the three
I can hear that.
Alright, good.
Okay, good. Continue.
outcomes
Alright, okay, thank you, Doctor.
I hope to achieve by end of this slide, the end of this slot basically. Okay, and then over here what I want to show to you is who dislocates the tensile strength of the metals, because we seems to understand how metals deform. So before I proceed, I'll just recap or basically state to you what are the expectations for today's slot. This chapter is quite a big chapter, but in this slot, I would like to touch on three things, basically on edge and screw dislocation motion, okay, from atomic perspective, and to describe how plastic deformation occurs by the motion of the dislocations in response to applied shear stress. So the key word here is motion, movement. And then we will talk about slip system, what it is, what it consists of, and then we'll cite example and relate to the materials property basically. All right, so those are the three outcomes I hope to achieve by end of this slide, the end of this slot basically. Okay, and then over here what I want to show to you is how these locations, how these locations move in metals compared to covalent ceramics and compared to ionic ceramics. You know that metals, they bond by metallic bonding, and the bonding is actually non-directional, right? There's no restriction to where the nucleus sits and to where the electron cloud sits. Basically, they are free flowing inside the material. For covalent ceramics, things that are bonded covalently, right? You know that covalent bonding is directional.
Azwan, I don't see the slide.
Okay, the arrangement of atoms, how the atoms sit in respect to each other, with respect to each other, depends on how many atoms are sharing electrons with the material. Right, so you must know that covalent bonding is directional. So there is an angular direction, how the molecules can arrange themselves. For ionic, the condition that you have in the material is that you have different charges. So you need to maintain the charges to be neutral, right? Otherwise, your material will be charged. So if it is a neutral material, then whatever you do to the material, it has to maintain that neutrality. So for dislocation motion, you know your edge dislocation and screw dislocation, they can move, all right? This is what I'm telling you now. They can move actually, and you already know that, I believe, from chapter 4, right? The movement seems to be much easier if they are in metals, because there's no restrictions on the bonding, no direction, no charges to maintain neutrality and so forth. But the motion will be a little harder in covalent bonded material and also in ionic bonded material due to the nature of the bonding. Is either directional or due to the charges. So it affects the motion of your dislocation. In here, just illustrate, okay, how that movement of edge dislocation, because you have edge dislocation here at location A, with the application of stress, okay, and this is shear stress that we are talking about, right? So on one side, it is pointing to the right, on the bottom side, it's pointing to the left. So in this kind of stress, right, you're going to cause this edge dislocation to actually move one atomic spacing to location B. What happened is that these bondings are broken and they were bond to the new sets of half plane there, so that it becomes now connected. You see, the bottom part now connected to the upper part of A. And now that the edge dislocation has moved position to be at location B. So you can imagine that this process continues on, whereby now this one will be broken, the bonds will be broken, they will form new bonds with this new edge dislocation. So now it is connected to this bottom one, and you're going to have these things to continue on propagating, breaking the next bonds, you know, and until the end. What happened is that your extra half plane ended at the end of your crystalline block. So this is how dislocations move. But of course, this happens in very, very, very fast, in a very short time. So you must appreciate that, because these things are at a minute level, very small level. So it happens very, very fast. So the idea here is that for deformation to occur, if you want deformation, your dislocations must move. And what does that mean? If dislocations move, means the atoms are moving. All right. So again, if you want a permanent deformation, if the deformation is permanent, that means it's plastic deformation. This is what we call plastic deformation. Okay, plastic means permanent deformation. So in order to get that permanent change in shape, you see, you are changing the shape permanently here, you need to cause the dislocations to move. All right, and how do you do that? You move the atoms. So that's the idea, that is the concept of what we call slip. All right, slip is when you have plastic deformation by the movement of the dislocation. All right, so that is slip. You have permanent deformation by the movement of the dislocation, causing that plastic deformation. So that's what we call slip. Okay, then what happened? Here it just show in schematic manner, a different view about the dislocation motion. And once the dislocation moves, you must see that the movement takes place over a slip plane, over some plane, and in some direction. So we call this slip plane and slip direction. Okay, and they form what we call what we call slip system. What is a slip system? A slip system consists of slip plane and slip direction. What is slip plane? Plane over which the slip happens, or the movement of the dislocation happen. And slip direction is the direction over which the dislocation moves. So let's see what happened in edge dislocation. Okay, so you have this extra half plane on top. There's no extra half plane below, right? It's not connected to the below atom. So you got edge dislocation here, and the direction is shown here. right? And the shear stress is applied. You see, one is in right direction and this one is on the left direction. So if you can imagine that you are trying to pull this block in the two opposite direction, you're only going to cause this edge dislocation to move. All right, what happened? It will just move in that direction. Okay, and at the end of it, you're gonna have a new shape of your block. Okay, now you got extra part over there. Initially, you see there's nothing here. Now it comes out at the end. So this is permanent deformation. Okay, so take note that the direction of the slip direction, right? The direction over which your dislocation moves, it is moving in this direction, which is parallel to the shear stress, applied stress, right? And the plane over which the edge dislocation moves is what we call the slip plane. So every time slip occurs, it must happen over some sort of plane, okay, and some direction. Okay, so in edge dislocation, the direction is parallel to the shear stress. The plane is also parallel. I can say that it's parallel to the direction of the applied shear stress. Okay, but where is the dislocation line? Dislocation line is this direction. Okay, so the movement is actually perpendicular to the dislocation line. But in terms of shear stress, it's parallel. So don't get yourself confused there. Yeah? Ini perpendicular to the dislocation line. So dislocation line is along this line. So applied stress in that direction. So it's perpendicular. The motion movement is also perpendicular to the dislocation line. But a little bit different in screw dislocation. This is where you have your screw dislocation, okay, a displacement of the atoms, okay, as shown here. But when you apply your shear stress, okay, what happened is that you can imagine this going to tear to the back, okay? It's going to tear off until to the back, right? So at the end of it, you're going to have one step like this in the crystalline structure, okay, in the crystalline block. All right, so you got permanent definition over here. All right, so in this case, what happened is that the dislocation line, okay, it's where is the dislocation line? Dislocation line extend here. Remember your screw, the screw dislocation. So along this line, all the atoms are misaligned. So this dislocation line now is parallel to your shear stress. Okay, but the movement or direction of the motion of the dislocation is perpendicular to the dislocation line. Right? It's just that the direction with shear stress is different from here. All right, so that's what it's all about the dislocation motion. Okay, so they can move. Dislocation can move with the application of stress. All right, so over here we want to talk a little bit more about slip system. So just now I said slip system consists of a slip plane and slip direction. Okay, so it cannot happen on just any plane or any direction, right? The plane over which slips happen or over which dislocation moves is the plane with highest planar density, the ones that have the highest arrangement of atoms, lots of atoms sitting on that plane. So that would be the probable plane for the slip to happen, right? And then in terms of direction, it also happened in the highest linear density direction. That means that direction is fully packed with atoms. So you might feel that, why is it so? It's because if I have a direction going that way, where you have atoms touching each other, it is fully packed or close packed. So it's easy to move, one atoms to another place and another place. If it is empty there, then if I want to move this, it just got stuck in this hole. So it just then remain there. But over here, if I push it, it will just push this to this part, and this part will push it to the other location, and so forth. So movement is easier when you have close pack, when things are touching each other, when the atoms are touching each other. All right. So if there are lots of vacancies, lots of voids, and that one will not help your dislocation to move. That's why the condition is to have the highest planar density and highest linear density. This is the reason you learn about planar density before and linear density in chapter 4. All right. So what is D? D is just the interplanar spacing between two planes. Okay, planes HKL. So the distance between two similar indices plane would be A, the lattice parameter, over the square root of the total sum of the indices, H square plus K square plus L square. So the wider the interplanar spacing, it indicates as the higher planar density. All right. So for FCC case, if we can draw it here, you can see that the highly dense plane would be 1, 1, 1 plane, because you see over here atoms are touching each other, over here also atoms are touching each other, here also is touching each other. So this is the plane of the highest density. It doesn't mean it's one, but it's the highest among any other planes in FCC. So the direction is also fully packed along all these three sides. Okay, therefore we say it is 111 planes with close packed direction 110. This combination gives you 4 planes and 3 directions. So in total, it gives you 12 slip systems in FCC. So it's kind of fixed. Okay, when you talk about FCC, the number of slip system is 12. So it's fixed. In BCC, the combination is between 110 and 110 direction, 211 and 11, 321 and 11. You can check it out, okay? But we are already telling you that there are 48 systems. So you can play around and see whether these are all the fully packed highest density planes and highest density direction. But there it is. You got 12 slip system for FCC, 48 slip system in BCC. So it's all prescribed. It's already predetermined because of this condition. Okay? We know already that it only happened over the most dense plane and most dense direction. That is the reason. Okay. However, comparing FCC with BCC, okay, which one would be easier to deform? Which one is softer? Normally, it's easier to deform in FCC compared to BCC, although they have many possible slip systems, because the amount of stress required for this 48 system, okay, to operate is high, right? Although in FCC, you only have 12 slip systems, but the critical resolve shear stress, or the stress required for the dislocation to move, right, is much lower in FCC. We'll talk about that later, okay? So over here, we illustrate to you about the 4 different planes in FCC, okay? 111 plane, 11 -1, -111, 1 -1. So all these are the family of 111 planes. And then you know that the direction is in terms of 101. So it can be negative, negative in X, negative in Y, and negative in Z. So you got the three variations. So every plane will have three directions. So four planes times three direction, you got 12. So this is how you got 12 slip system for FCC. Okay, so similarly for BCC, you can convince yourself that in here 1, negative 1, 0, you have direction 111. Here you got plane 1, negative 2, 1 with also direction 111. So normally in BCC, the highest density direction is 111. We fixed that. That one is already known. So that one is not changing. All right. Only the most packed crystalline planar density is changing. So when you count this, okay, 12, 12, and 24, you got 48. You can try to do that and check whether what I say is correct, but I'm telling you it's 48. Okay. All right, so that's all at the moment. This is just to introduce you to the concept that dislocations move with the application of stress, right? And then the concept of slip system and what it is, combination of slip plane and slip direction. And also you need to know that in FCC there are 12 different slip systems. It happens over 111 planes and direction 110, while for BCC it happens on these types of combination with 48 system. That is what you need to know at this point. Okay, so after this we will continue our discussion about dislocation. We are going to analyze the dislocation motion a little bit further, whereby we want to know what is the stress required in order to make the slip happen. Okay, so crystal slip due to a resolved shear stress. So we want to know how we can analyze this problem so that we can understand how much stress is required in order to cause that slip. But that will be for the next lecture, okay, in the next slot. So thank you so much for listening. Okay, hang on. All right, so that's all for now. We will come back to you with another topic. All right, thank you so much. See you soon. New about on our topic on dislocation.
How do we calculate the slip system?
translated about on our topic on dislocations and strengthening mechanisms, right? So in the last lecture, we were talking about sleep system. So by now you should be able to understand that when sleep happens, it happens on a sleep plane and in sleep direction. So those two, plane and sleep, combine as a sleep system. And it does not happen just on any plane or direction, but instead it only happens on the highest packed plane and the highest packed direction. All right, so that's the highest linear density and highest planar density. So we gather that for BFCC, we have 12 different sleep systems, while in BCC, we have 48. Right, that's just a recap from last lecture. So what we're going to continue now is to analyze our situation where we have our specimen here, and then we apply force. Of course, this force can be translated into shear force, on shear stress and so forth. And you realize that we take a cylindrical specimen with cross-sectional area of A, and we say that this is the direction of the sleep. So this is the sleep plane, all right, and that's the direction of sleep. So that's the direction either way lah. You can see it in either way. So when I want to analyze this, because I want to know how much stress is required for sleep to happen. All right, so I just bring out the sleep plane. Okay, this is the sleep disk basically. So one plane and another one. Now, when we analyze this, we have to translate this F and A, onto this sleep plane. Now, the resolved components of F now becomes Fs, that is on the sleep, okay, force on the sleep plane. And then we have area on the sleep plane, right? And then we have normal to the sleep plane. We define all these things, right? And then we have shear stress. Okay, this is called the resolved shear stress. Okay, in the direction of the sleep, because the sleep happens due to this component, basically the resolved shear stress from the applied normal stress. Okay, so having all those details about our specimen, then we know that resolved shear stress is equivalent to Fs over As. Right, this is just force over area, but of course we need to take the area on the sleep plane and area on the sleep plane. Okay, it's not that normal area. This the perpendicular area to the applied force. So this is the component of area for on the sleep plane. So this is the area of the sleep plane. Now, when we fill in, we find out what is Fs, what is As with relation to the applied force and the original A. We will find that F on the sleep plane is equals to F with a factor of cosine lambda. Okay, so lambda we can define as the angle between the applied force and the resolved force on the sleep plane. Okay, on the you can say it in the sleep direction. Okay, and for As, okay, the area of the sleep plane would be equals to A, the perpendicular A is here, okay, divided by cosine phi. I call this phi, right? So phi is the angle between the applied force. This is the applied force F, the normal applied force, divided. Divided. The angle is between the applied force and the normal to the sleep plane. Okay. So that is normal to the sleep plane. So your sleep plane is the green one. That's the area of AS. The normal to this green plane is NS. So you got this relationship. Okay, you can work it out. I'm sure this is just simple mathematics, all right, with some theorem. So when you replace that into this equation, you get this big equation, very important equation in this chapter. It says that the resolved shear stress, that means the shear stress that acting on the sleep plane, okay, in the direction of that sleep direction, right? The resolved shear stress is equivalent to the applied force, whatever you apply here in terms of A over A, okay, F over A, and multiply with a factor cosine lambda cosine phi. And you know that lambda is the angle between the applied force or the stress, applied stress, and the force on that sleep direction. Okay, and phi is the angle between the applied force with the normal to the sleep plane. So you got this equation, memorize this equation. All right, so that is the relationship between the resolved shear stress that you experience on the sleep plane and the applied force sigma. That's the relationship, okay, by the factor of cosine lambda and cosine phi. Now let's look at that equation, a little bit more, okay. This resolved shear stress, right, it has to be greater than the critical resolved shear stress for the sleep to happen. Okay, that's the condition for dislocation motion. So the value of this shear force, resolved shear stress, must be of certain value. It must overcome a minimum value, then only it will sleep. So what is that value? We call it CRSS, critical resolved shear stress. The value is typical value will be around 10 to minus 4 gigapascal to 10 to minus 2 gigapascal. Okay, so later we'll see how you find out what is the tau CRSS for each material. Okay, now just have a look at this equation. All right, we just want to analyze the extremes of this equation. Now, let's say that you have a specimen, you apply sigma, okay, there, or F lah ni kan, F over A. So you apply sigma, and if your sleep plane is perpendicular to the applied force, what happened? Will you got sleep? Okay, so if the angle between the applied force and the sleep direction is 90 degrees, that is saying lambda is equals to 90, cosine lambda is 0. All right, so when cosine lambda becomes 0, tau resolved, tau r becomes 0. If it is 0, then you got no energy to sleep. Okay, so no sleep in this case. You cannot sleep. How about in this extreme, when your sleep plane is actually oriented parallel to the applied sigma? All right, so now over here phi is 90 degrees, right? Because phi is the angle between the applied force and the normal to the sleep plane. So this is the normal of the sleep plane. So that angle is 90. So phi is 90. Again, cosine 90 degrees is 0. Therefore, again here, your tau r becomes 0. If it's 0, no energy, you cannot move anything. So you don't sleep when you step on a banana right on, perpendicular. Okay. And if it's totally parallel also, you will not sleep, right? But in this case, what happens if both lambda and phi are 45 degrees Celsius, 45 degrees, all right? So let's say the plane is like 45 degrees. This is the sleep plane because, sleep plane is already selected, right? So in this case, you're going to get maximum because cosine 45 is, what is cosine 45? It's half kan? Half, 1/4 tak? Kedua, 1. Betul lah half, okay? Over 1 over square root 2 kan? Okay, so in that case, when you got this situation, tau r becomes maximum, right? That is sigma divided by 2. Betul ke? Saya pun dah lama dah. Cosine 45. 1 over square root 2. Okay. So your cosine would starts from here kan. Okay, so that's 1. That's negative 1. 0. Right? So I think you can get that. So this is the situation. You must realize this, the extreme. All right. The maximum tau r would happen when the two angles are 45 degrees, and that will give you half of the applied force. So the half of the the stress would be acting on that slip plane. It will slip because it's already maximum. Okay. So what happened here? What we show you here is about the single crystal. How do they slip? Single crystal is, having all the orientations of the atoms in the same direction. Okay, if it is a cubic, and then the cubic is pointing along the same direction, no different direction. So in that case, when it slip like a step like this. Okay, because this is maybe 1, 1, 1 plane, and then this one is also 1, 1, 1 plane. Everything is 1, 1, 1 in the same direction. All right. So this is how you observe in reality when you have slip in single plane, in single crystal. All right. So what happens if it is a multi crystal, or you have a polycrystal? When you have polycrystal, if you can remember, you have lots of grains. Okay, each grains. Okay, these are all grains, kan? The grain boundary and all. Each grain will have its own 1, 1, 1 direction. So maybe that slip is in that direction. In this grain, the slip plane may be aligned in this direction. In this grain, it may be along this line direction. And this one may be something like that. So within a grain, it will be behaving as if it is a single crystal. But of course, it does not continue throughout the material because you have grain boundaries. It will stop at the grain boundaries. So you don't observe this single step, parallel steps like this in polycrystal. All right. Okay. Now let's observe some of the factors affecting slip motion. Okay, so we're gonna compare between FCC and BCC. HCP, you just just look at it. We are not going to deal with HCP because we didn't learn about the crystal structure anyway. Right. So how about the critical resolved shear stress? That is the minimum tau that you must achieve in order for the system to slip. All right, so then there must exist this minimum value. Okay, for FCC, the value is 50 to 100 psi, pounds per square inch. But when you look at BCC, it is 5,000 to 10,000 psi. So such a huge difference in terms of the minimum shear stress that is required for slip to happen. So this is the minimum for slip. Okay. Now, number of slip system in FCC is only 12, but BCC got lots, right? So, but it does not matter because even though you have more here, 48, but if the value required to slip is so high, the stress required, the shear stress required is too high, then the property becomes strong because it's difficult to move your dislocation. Okay, you cannot cause sleep to happen easily. You need to reach this value before it can sleep. Therefore, your material become strong or stronger than FCC lah. Because in FCC, although you only have 12 operating sleep systems, but the value of the tau CRSS is rather small. So many sleeps can happen although it's just within 12 systems. So that is good enough, making it a ductile material. So any FCC material would be ductile and any BCC material becomes very strong on the basis of this sleep motion. Because, when we talk about ductile, we talk about being strong, high strength. It is about how they resist the application of load, again, about stress. So this is the explanation why FCC materials becomes ductile. So you can explain in terms of the lower tau CRSS that they experience. Okay, although their sleep system is not as many as in BCC. Cross sleep means you change direction. When you sleep, just like in the polycrystalline, right? Let's say you sleep over here, you move into that direction. You move in that direction and suddenly you face a grain boundary. So what do? You can cross sleep. You can change direction. Now you say you're going to move in that direction. If you hit another boundary, let's say this one will hit this boundary. So it will continue in the different direction. So that's what we call cross sleep. So they lompat into another boundary. So for FCC, it can happen. For BCC, can happen. So you cannot compare lah, right? But for HCP, no. So not all crystalline structure would allow cross sleep, right? So, okay. Now let's have a look at one example and see whether it makes sense to you, right? So the question is that you are given this situation, all right, where you have a single crystal, and to remind you, when we have question, it's normally about single crystal because it's more complicated if we analyze polycrystalline, all right? So we limit our discussion into single crystal, but you can imagine your single crystal sits within the many different polycrystalline too, okay? Every single grain can be analyzed as a single crystal. Now, the question is, with this kind of loading, okay, F, okay, is the sigma is given as 6,500 psi. The angle of phi is given, the angle of lambda is given. Remember, don't switch these two together. Yeah? Lambda is the angle between the applied force and the sleep direction. And phi is the angle between force, applied force, and the normal to the sleep plane. So don't get that confused, because once you get that confused, everything else will become wrong. So with this kind of schematics, apa benda the design of the applied force is given, will the single crystal yield? That's the question. Okay, so you must be able to analyze this situation and tell us whether yielding will happen. What means yielding? Yielding means, on your stress and strain curve, when you pull and then ni kan. So yielding is the point where you start your plastic deformation, sigma yield. So we always refer to the region where you start to deform plastically tu, kita panggil that sigma yield kan. So this sigma yield is what we are referring here. Will the crystal yield? Will the crystal sleep? Will the crystal plastically deform? So many terms we can use, but you must understand, when it yield, that means it is going into plastic deformation. When it yields, that means it's sleep. Okay, jangan tidur sudah. Okay, this is sleep. So how do I know whether it is going to sleep or not? I have to use this equation, because this will tell you what is the value of your tau. Okay. So given tau CRSS, the minimum value is 3,000 psi. So my tau resolve must be, otherwise I cannot sleep. All right. So lambda is given Okay, lambda is given, phi is given, masukkan dalam equation, you will get your sigma is also given in the question. You will find that your tau resolved shear stress, right, is 2662 psi. Now, this value, your resolved shear stress ni, RSS lah, bolehlah tuliskan. Alright, is actually less than the minimum value required for sleep, which is 3000 given in the question. Alright, because of that value less, okay, I will not sleep. I cannot sleep. I cannot cause the material to yield. Okay, so the applied stress will not cause the crystal to yield. No sleep, no plastic deformation. If not, what stress is needed? Okay, tell me then, what is the required sigma for me to ensure that I can deform this material? Okay, deform this specimen. So in order to do that, okay, we need to find out, okay, you can either, what do you do? Okay, then I have to know what is my sigma yield. Okay, that will give me an idea about whether it is going to sleep or not. Jadi what do? I use the value given because this is CRSS kan. So this is the minimum value that you must have in order to cause sleep. Okay, so this value is known, the resolved shear stress to known. This one is the critical resolved value. Lambda is known, phi is known. Jadi now I can find out what is my sigma yield. So when I solve this, I find that my sigma yield, okay, should be 7325 for the deformation to happen. Okay, so if the material has that value of sigma yield, then only it can cause deformation. All right, so I think that's very not that difficult to understand, but this is a good example to demonstrate whether you understand the concept of this sleep system, the concept of critical resolved shear stress. And this equation this big equation I mentioned to you, all right, has a name. This is called SCHMIT law, Smith's law. That's what we call it, Smith's law. I hope I spelled it right. Okay, Smith's law. Nampak pelik sikit. So these two things, cosine lambda and cosine phi, is called Smith factor. Smith factor. Okay, so Smith yang discover this. All right. So if you want to put your name on equation, you need to discover new things now. All right, so that's about deformation of a single crystal where you apply the Smith law in order to analyze the value of tau. So tau ni basically you want as high as possible lah to ensure deformation happens. Okay, so this is what I mentioned just now about in polycrystal ni. Wow, okay. Polycrystal, this is how you see the grain. You see one direction here, another direction, another direction. They all have in different direction. So within one grain, that would be one single crystal lah. Ini there's one single crystal. Here's another one single crystal. This one is single crystal, and in here also there's one single crystal, and so forth. So your Smith's law is applicable in this region by itself, here by itself, and separately. All right. So what happened in polycrystal? Very interesting because you have lots of grain boundaries. So it becomes stronger. When it faces the grain boundaries, it got blocked. Okay. Although it can cross slip, that means you need more energy lah to cross slip. Therefore, overall your polycrystals become stronger because you got a lot more hindrances, lots more obstacles to stop the movement of the dislocation. So basically understanding that movement of this location, I just put the symbol. Okay, movement of dislocation will cause the material to be ductile, easy to deform, easy to deform. But if you block the movement, anything that will block the block the motion of the dislocation, then you can get a strong material. Itu je konsep dia. That's very simple concept. Okay. Now, so because this polycrystal, they have lots of single grains, so they have their own slip plane and directions, okay, in each of these crystal. So keep changing lah. When you move from one to another, it keeps changing. Therefore, tau R will vary from one crystal to another. So this tau R here would be different than the tau R here because the value of this keep changing. All right, the crystal with the largest tau R will yield first. So if in here I got 5,000, 5K, over here I got 10K, all right, over here I got 2K, okay, which one will yield? The highest one will yield first, okay, the one that have a highest resolved shear stress, because you say there's lots of energy here, you are given a lot of energy in this crystal due to the orientation and so forth, so this one, the slip will happen here first, right, then only the others would be activated. Macam itulah, you must understand that. Yeah. Say others less favorably oriented crystal will yield later. Right. So that is the concept of the Smith's law, and I will stop here. This one wraps up on the Smith's law. Okay, you must know how to apply the Smith's law and to solve problems related to this slip. Okay, that's it. Thank you very much. I hope it makes sense to you. All right, I see you in the next video. All right, thank you so much.
Okay, we have already completed 2 parts. So I think some of the questions have been answered. Dennis, so if the shear stress equivalent to CRSS shear stress, then it can yield, right, Doctor? Yes, exactly. Sir, Y lambda plus phi is more than 90 degree. Lambda plus phi is more than 90 degree. All right. What do you understand about lambda here? What do you understand about phi here? Okay, as per discussed earlier on. So you need to check back. Okay, you need to understand well about lambda. You need to understand well about phi. All right. It's not exactly have to be in this particular question. What the question mentioned to you is that 35 degree and 60 degree. So plus 2, it will be equivalent to more than 90. So it doesn't have to be that. It depends on the questions given to you. Sometimes it can be less than 90. It can be more than 90. All right, Wong? Okay. Okay. If you don't understand, it's okay. You keep that one first. We'll continue with the next part.
about strategies for materials strengthening. So just to recap again, the important concept about dislocation. So we have been talking about dislocation. We learned about that in chapter 4, but their motion is what is important in causing slip to happen. And what is slip? Slip is permanent deformation. Permanent deformation. So when we say permanent deformation, what strikes in your mind? This is actually what we say plastic deformation. Use different terms, different terminology, but then you must understand what it is all about. Yeah. So in order to cause permanent deformation, I got to cause slip to happen. Slip is by dislocation, motion. So when slip happens, it has to be on certain plane. Okay, on certain plane and in certain direction. So the idea is that if we want our material to deform easily, being ductile, being malleable, then you need to assist with the dislocation motion. You have to make it easier for the dislocations to move. But if you want to strengthen the material, right, what do you have to do? You have to block the motion. Okay, this motion has to be blocked or hindered, or you need to put obstacles to it. Anything that you can do in order to block or make it difficult for the dislocations to move, that means you're going to strengthen the materials. So in this case, okay, what we're going to look at, there will be three methods, three strategies. One is to reduce grain size. Another is to have solid solution. You have seen this in chapter 4. And also by having cold work, or what we call strain hardening or work hardening. They are all the same thing, but they have different terminologies. So we can do one of these three in order to strengthen the material. So now the issue is to see and to explain how reducing grain size can actually strengthen your materials. All right. So what we need to realize is that grain boundaries themselves serve as barriers to slip. You see, so in this crystal structure, you can see there's a grain boundary here. Why I say there's a grain boundary? Because it separates the two sides. This one orientation is pointing that way, you can see it, and this one is like, in different orientation. So you have two grains here with different orientation, grain A and grain B. They are still in the same material, they still have same crystal structure, but orientation is different. So when you have grain boundaries, okay, the more grain boundaries you have, that means you're gonna impede the motion of your dislocation. So look at this dislocation, trying to move through. So it can move through this grain until it hits the grain boundary. It's going to face some difficulty there. If you don't give it enough stress, enough energy, it will not be able to cross slip and continue moving. All right. So grain boundary is going to give the obstacle, will be the barrier to slip. So if you have small grains, right, you're going to have lots of grain boundaries, and that's going to be more barriers to slip. Therefore, it's good to have smaller grain size so that your material becomes stronger. Okay, that's one way. Another way, which we have seen that basically, is to have solid solution. What is solid solution? Solid solution means you have foreign matters. You have different types of atoms inside your material. So you put in what we call maybe impurity atoms, all right? Or we can call it just foreign atoms. Impurity means something you don't want, okay? Foreign atom, maybe you put it, okay? You intentionally put inside the material, like having an alloy. So this solid solution is basically alloying, Okay, you put a new material, a new element inside your material. All right, so this is what happened during alloying. That's why you say when you alloy things, your material becomes stronger. Okay, so what happened is actually it distorts. Okay, distorts means you change the dimension, the shape of your lattice. Okay, and also by doing that, by having that distortion, you also generate stress internally. Okay, so stress can produce a barrier to dislocation motion. Of course, stress is like a barrier because it's not normal. Okay, it's not neutral. So something is different inside your material. So let's see what happens if I have an impurity. If my impurity is small, all right, a small impurity there, somewhere inside there, what happens is that the atomic arrangement tends to like shrink in. Okay, it tends to move in. So still, then you're going to create some stresses around that area. Okay, all this area is going to experience stresses. Okay, but these stresses is like pulling inside. Okay, going to compress the atom inside. Okay, so the rest outside metals would be strained, would be pulled towards inside. So they have stresses around. Okay, what we call local stresses. All right. And when you try to push your dislocation to the right, it will definitely interact with the dislocation and giving some difficulty for that motion, right? So, and hence, you're going to have strengthened the material. For a larger substitutional impurity, similar thing is happening, although now the atoms is bigger than the host atom. It's going to put compression onto the surrounding, all right? And still you're going to have local stresses around that impurity because you see your lattice is now strained, okay? It's not just like normal lattice. Therefore, it's going to interact with that dislocation motion and giving it some difficulty to proceed. So it has to overcome the stress, okay, in order to travel through. So again, your material becomes strengthened, right? So if we look at dislocation itself, this is the area of dislocation, how all these stresses is developing. Okay, if it is edge dislocation and your extra half plane is on top here, all right? So what happened is that this is like causing compression to the nearby atom. So it is like pushing out, okay, compressing onto the surrounding atom. So you have compression stress on top, while at the bottom you are straining it, you're trying to push it apart because over on the top there's extra line of atoms. So bottom is experiencing tension. So your lattice is no more neutral. Your lattice is under some stress, okay? Ada compression stress, ada tension stress, right? So it causes lattice distortion or lattice strain. Again, it will impede the motion of the dislocation. Okay, this is what I mentioned just now about alloying. Okay, this is just to demonstrate to you what happens if you have a smaller solute atom inside the host. So all these are the hosts. Now this is small. Because it's small, you tend to pull in. Okay, the surrounding atoms will pull in. That means they will be under strain, right? And pressing onto the impurity or the foreign atom or the solute. Okay, so what happened? Because it's small, it's going to relieve some stress on top of that edge dislocation. Remember here you have compression and below is strain. So what happened? Your alloying element, your solute atom, because it's small, is going to partially cancel the compression stress experienced on top here. All right. So they put 3 here. So basically you are cancelling some stresses over here. Here is still under compression, you see, compressing. But over here they released because you got put 3 smaller atoms there. So that's what we call partial cancellation of the impurity dislocation lattice strain. Okay. Although it is releasing the stress there, okay, it's like a driving force lah, because over here the compression, so your impurity likes to be here, your foreign atom likes to be here to cancel the stress on top, okay, but still this is going to reduce the mobility of the dislocation, and hence you are increasing the strength. Okay, kalau if you have a bigger solute atom, what happen is that, you see, it is going to impinge, they impose compression onto the surrounding atoms, and now that big atom will not sit on top because here is already compressing, so don't want more compression. Right, so you will tend, these two host atom, the solute atom will tend to gather at the bottom side of the edge dislocation because the bottom is experiencing tensile. All right, so here now is compression, so of course opposite attract, so they tend to be at the bottom side and release that stress a little bit, the tension a little bit here. All right, so that's what we call partial cancellation of the impurity dislocation lattice strain. And all this in effect is to reduce the mobility of the dislocation, and hence you increase the strength. Okay, all right. Okay, now moving along, this is to show you a particular example of solid solution strengthening in copper, where we include nickel inside. You see, the more nickel content that you put into the copper, the tensile strength tends to increase, right? And the yield strength also behave the same way, it increases, right? So it's by this empirical relation lah. And the yield strength is proportional to the composition to the power of half. Okay, so basically alloying increases sigma y yield and also tensile strength. And of course, when the strength is increased, you know that ductility will decrease. When we talk about ductility, we are talking about percent elongation from chapter 6. Elongation will also reduce. All right, so everything is connected, everything is related to microstructure and property relationship too, so you must get that one. All right, moving to the third method, strategies is about cold working, about strain hardening, about work hardening, all are talking about the same thing. What is happening here? Okay, this is a concept where metals becomes harder as they are plastically deformed. The more deformation you give to a material, right, it becomes harder, it becomes stronger. That is the concept of cold working. Okay, and when we say cold working, we are referring to room temperature. That means whatever we do rolling, we do forging, we do extrusion, we do drawing, everything is happening at room temperature. Remember, we are dealing with metals, but still we are doing it at room temperature. Some metals have lower melting temperature and they can be cold work. Okay, so you can do work onto the metal piece at room temperature, and hence we call it cold working. But of course, you're going to damage the microstructure. You're going to change the microstructure, not necessarily damage. Maybe sometimes you want to work on the metal. Okay, common forming operations can change the cross-sectional area, include, as I mentioned earlier, forging. What do? You have a mold, you put your blank, this is your metal blank, and then you close your mold, you put force, therefore your blank now have that shape of the mold. All right, rolling is just using rolls to change the diameter, to change the shape of your metal piece. And in drawing, you basically pull, you have tensile force, you pull through your blank, through the die that will take the shape of the die or the diameter that you set. And extrusion is something similar, but you push and you extrude, so you push it. This one you pull, right? So again, there's always a die to give you the dimension that you want or the shape that you want. So these are the four common fabrication techniques for metal, and we do that for coal working. We can do all this thing at high temperature, but now we are talking about coal, right? And how do we measure how much work that we do onto the metal specimen? We have this calculation of percentage of coal work. This will measure how much deformation, how much deformation you have made to the sample, and how much, I can say maybe dislocation, when you roll all this thing, you forge, of course you're gonna flatten the microstructure. All these are grains, right? And these grains will become like damage when you roll it, when you forge it, when you do work onto it. So, this is going to affect the properties of the material. And for first, initially we need to calculate how much percentage of coal work are we giving to the material. That means it's how much damage, basically, how much dislocation we are installing inside the material. How we measure that? We take the initial area minus the final, the deformed area divided by the initial area. You can do this for area, you can do it for diameter, you can do it for length, you can do it for width, you can do it for height, whatever. Okay, so you can you can follow any of these dimension, and then you can count how much coal work you are putting inside the material as you work on it. All right, very simple formula, and this is, if you remember, this is the same formula for strain, right, for calculating strain. So they are all connected. This is how you calculate ductility. They are all connected. All right. Okay, so right? So what happened when you do coal work? You see, you're gonna put a lot more dislocation. Jangan gerak. You're gonna put a lot more dislocation inside the material because you're working on it. You are damaging the grain boundaries, the grains, and you are creating more grain boundaries. You're gonna create more dislocation inside. So it looks all messed up. It's all entangled. You can see all the grain, all the dislocations are all tangled up. So it's good because now they are not moving. Okay, if they are tangled up, dislocation entangled during the coal work, dislocation becomes more difficult. Therefore, it gets strengthened. That's the idea. That's the reason why we do coal work to a material, because we want to strengthen it. So what happened is that the dislocation density has increased during the coal work. All right. What is dislocation density? Okay, density again. Okay, the concept of density. Now it is talking about total dislocation length divided the unit volume. So this is 3D lah. Okay, so if you add up all the length of dislocation divided the volume, you're gonna get your dislocation density. For a carefully grown single crystal, just for reference here, the number of density, dislocation density, can go up to 10 to the power of 1,000 per millimeter square. This is in terms of, because the unit is length over here and volume, so you get per square area. Deforming sample increases density 10 to the power 9 to 10 power 10. So from 3 power 3 to power 9 power 10. If you do heat treatment means you heat it up back, your sample, you take this sample and you subject it to heat, adalah at certain temperature for certain time, okay, and then you cool it down. What happened? That heat treatment can reduce the number of dislocation again, okay, to 10 to power 5 and to power 6. So all these things are recyclable, in a cycle lah. You can increase the dislocation density, you can decrease the dislocation density by doing the right thing. All right, so if you want to increase the density to increase the strength, you do coal work. If you want to remove because there's too much density, now it becomes too much dislocation inside, becomes brittle because too hard, too strong, it becomes brittle, you want to reduce that, you do heat treatment, right? So engineers can do all these things. That's why we are here, we need to solve problems. Whatever people need, we come to their service. All right. Existing dislocations, grain boundaries, scratches are possible sites for dislocation formation. So all these areas are defect areas. They have high energy. So normally they becomes the location for dislocation formation. All right. All right. So what happened to our yield stress? Yield stress increases as the density for the dislocation increases, because the strength is increased now. You see now you have a higher yield stress. Okay. So this one is small hardening. This is large hardening. Okay, I hope you are following. Okay, I got a few more slides on this just to illustrate more about dislocations. We need to understand dislocation more, get to know how they behave and so forth. So it seems that, okay, dislocations, okay, they have that lattice strain, okay, and they actually interact with each other, with one dislocation with another. You see, this is one dislocation, and the top is compressed and below is strain. Okay, and if you have another one next to it with the same orientation, compress and strain, the same direction here, of course this will repel. See, they work like an ion, like ion, like ion. Right, so they will repel. So this one you have repulsion. If they are on opposite, okay, one is compressed on top, one is compressed at the bottom. Okay, what happened? They will attract each other, right? When they attract, they will cancel out, because one is compressed on top, one is compressed at the bottom. At the end, they come together and they cancel out. No more dislocation. Perfect crystal. Beautiful. All right, so they can interact. So that's behavior of the dislocation. With the same orientation, compress and strain, the same direction here, of course this will repel. See, they work like an ion, like ion, like ion. Right, so they will repel. So this one you have repulsion. If they are on opposite, okay, one is compressed on top, one is compressed at the bottom. Okay, what happened? They will attract each other. Right, when they attract, they will cancel out, because one is compressed on top, one is compressed at the bottom. At the end, they come together and they cancel out. No more dislocation. Perfect crystal. Beautiful. All right, so they can interact. So that's behavior of the dislocation. Right, I suppose here we just do, okay, the impact of cold work. As I mentioned, we already mentioned this. Cold work, work hardening, strain hardening. What are they doing? They are increasing the yield strength. They are increasing the tensile strength. Okay, but they are reducing the ductility or percent elongation or reduction in area. So we already mentioned this. Just to recap in terms of this plot here, you you can see a material with 4% cold work. The tensile strain, stress strain looks like here. This is 0, so it's lower. This is 4. Now you put 24 cold work. Okay, 24%, even higher stress strain curve. All right, so fantastic. It follows through with what we mentioned here. What is the tensile strength and ductility after cold work? So there is a plot actually, okay, versus yield strength versus cold work, tensile strength versus cold work, percent cold work, ductility versus cold work. All right, so this would be for specific material. So this is copper, you got that line, copper and copper. So the question is, once I do cold work to the material, okay, what is the level of cold work inside and what is the strength and ductility? So you use this formula, percent of cold work, you find what is the initial diameter, what is the final diameter, the deformed diameter, divide by the initial diameter. Well, this is not diameter lah, dia ambil area. Right? So sama je, everything will be cancelled out anyway, kan? So this one will be cancelled out. So when you calculate that, you do cold work to copper from 15.2 millimeter diameter, you reduce it to 12.2. Dah kecil lah, okay? Because you do cold work, you do rolling on it, you do maybe drawing on it, you do apa lagi, forging, whatever process you do to it, it becomes smaller. So when you reduce the diameter, okay, you calculate the percent of cold work, it seems that you have put 35.6% cold work. Then I'll check with the plot. And what is the level of yield strength do I have on my material now if I already put 35.6% cold work? So you just read off from the graph, 35.6, what's the level of tensile strength. So you read off, this is the value. Bukan tensile strength, ini yield strength, sorry. For tensile strength, you read again, what is the level of cold work, read what is the value of tensile strength. For ductility, okay, it's 7%. You can see this is negative slope. Yeah? So the more cold work, the lesser the ductility. So everything is in the plot. It's just for you to read and calculate that percent of cold work. All right, this is what we mentioned just now about heat treatment. When you actually put that cold work inside the material, sometimes you want to remove it. Sometimes it's too much, you want to reduce. So what you do heat treatment, you do annealing. All right. So during annealing, what happened is that there are 3 processes, okay, 3 annealing stages, okay, recovery, recrystallization, and grain growth. And what happened at the end of your annealing process, your tensile strength is now reduced. Go back to the previously, before cold work. And then this is ductility from lower getting higher. All right. So that's what happened. What actually happened during the 3 process. Okay, recovery is the first process when you do annealing. This is where you subject your material to temperature, high temperature, over here about 100 to 200. Okay, what happened is that you remove all the defects. Okay, whatever dislocation that you have in the material, now it becomes annihilated. And now you have a perfect atomic plane. So this is what happened during recovery. The initial stage of annealing where the temperature is not very high yet. Okay, just about, tengok material, what is the temperature. So annihilation reduces dislocation density. So dislocation density got reduced during recovery. And then you go into the stage of recrystallization. Okay, recrystallization will happen at a higher temperature. All right. What happened is that you going to remove all these your cold work grains. Yeah. What happened is on too much. you're gonna remove all the dislocation, all the cold work grains, okay, will be removed. After 4 seconds, you have this kind of outlook. Okay, and after 8 seconds, now you are recrystallizing new crystals. So yang ini, all these are the old ones lah. All right. So now you are creating new grains. Right. All cold work grains are consumed. Okay. So initially 30% cold work brass. Right. It may look something like this, and then you start to create new crystals. All right. When you start at 3 seconds, so new crystals will come out, and then at 4 seconds you got more crystal coming up. At the end of it, you got all new crystals. Okay, so that's what we do. What happened actually during recrystallization? New grains are formed, have a small dislocation density, and they are small inside, and they consume all the cold work grains. So that's what happened. And at the final stage of annealing, that is at higher temperature, 600 to 700. Okay, what happened? Your small crystals, just now the new grains that come out, they tend to join each other because you are putting it more temperature, heat, energy, and then you leave it for a certain time. So what happened is that now they become bigger grains. Okay, so larger grains consume the smaller ones. Grain boundary area is reduced, right? So they need to be optimized. Energy need to be optimized. So that's what happened in the third stage. The name also grain growth. So now you got bigger grains compared to the during the recrystallization. Okay, I guess this is the probably a final slide. Okay, this is the plot that we have seen before. Okay. And this is the microstructure that you observe when you cold work. All the grains are flattened, all are cold worked, right? And then new grains are coming up, but then the smaller grains now grow into bigger grains. Okay. And recrystallization temperature, that is the temperature where you're gonna cause that new grains to come up. And that temperature is actually between 0.3 to 0.6 of its melting temperature. So you never go beyond that TM lah. Yeah? Okay, so due to diffusion, annealing time, TR, function of the shorter annealing time for higher TR. So of course, these are all happening by diffusion. Atoms move by diffusion. The higher the temperature, that means your annealing time will be shorter lah in order to achieve these big grains. Yeah? Higher cold work, meaning you lower your crystallization temperature. These are all the factors that affect the recrystallization temperature. Okay, pure metals have lower TR due to dislocation motions. Easier to move in pure metals, hence you got lower recrystallization temperature. So that makes sense. Okay, right. So we come to the end of this slot. Basically, what we have seen the strengthening mechanisms. Okay, in metals, how we strengthen it by putting barriers to the motion of dislocation, put barriers to it. So how do we put barriers? There are 3 ways. By having something reduce the grain size, and then we do a solid solution, and then we do cold work. All these things will actually impede the movement of the dislocation. And at the end, we look at how we reverse the effect of cold work, the 3 steps, okay, the recovery, the recrystallization, and also the grain growth. Right. So that's what in a nutshell what we have covered earlier. We still have an example to do, but I stop here. We will continue in a bit. All right. So thank you so much. Assalamualaikum warahmatullahi taala wabarakatuh.
Okay, Alhamdulillah. Even though we have 4 videos, this is the third one. Since we are running out of time, which is 5 minutes after 2, I think we need to stop here. However, I will share all the videos, all 4 parts in the ULearn. So I hope this will answer Nur Ain Shafiza punya soalan lah. Alright. And then your task is about to watch the last part, the final part, by yourself. And then next week we will cover a new chapter. So before we ended the class, is there any questions for you to ask me? I think it is very straightforward information about today's lecture that we have previously learned about on how to check the mechanical properties, and now we are dealing on how to strengthening the materials by few strategies. I think we have already discussed during our during the video shows. All right. So if you have any problem, you can ask me or Dr. Putri through WhatsApp or maybe through this medium. So I think thank you so much for your cooperation. Thank you so much for your attention. So what is percentage call work? I forget. Oh, please review the video again. Afif, percentage coursework is what? Percentage coursework. I think you can see in the ULearn. Doktor nak tanya slide division, doktor akan tukar kat ULearn. Yes, I will tukar insyaAllah. Call work, yes, cool. Right. So thank you so much for everyone. See you again next week insyaAllah. Have a nice weekend and stay safe. The number of COVID is getting increased, so stay safe and take care. Right. Assalamualaikum.